Are you ready now? No? Okay. All right. So this is another Italian name. How do you pronounce it?
Which one?
Yours.
Manlio Valenti.
Oh, great.
And this is Giovanni Soldato.
All right. And the title of the talk?
First part of the problem.
Right. And there's our introduction.
Thank you very much to myself for the introduction. And thanks to the organizer for inviting me, having me here. All right, so I'm gonna talk a little bit about this joint work I've done recently with Giovanni. This is about the first order part computational problems, but like let me start very generally from a very broad perspective. Let's start from an arbitrary partial order. Say that you have two elements in the partial order, and you want to show that A is not below B. Well, how do you do that? Well, this is very general, but like a standard strategy could be to just show that there is a C which is below A and not below B, right? That will follow just by transitivity that A is not below B. In other words, this simply means that there's a C which is in the lower cone of A, but not in the lower cone of B. Right, so of course, right, like now the problem, however, is shifted. Let's say, like, how do we pick this C here? Like, so ideally, if you could have some sort of operator, some sort of mapping that maps A to C and analogously maps B to D in a relatively nice way, then you can essentially reduce the original problem to the problem of comparing C and D now. In particular, if you could pick C and D in some relatively nice way, so they are maxima with respect to some given property phi, they are maxima in their respective lower cones, then proving that C is not below D would imply that A is not below B. So the idea is that if you could essentially reformulate the original problem in terms of simpler objects, then maybe proving a separation could be easier. Okay, nice. But like in practice, what do we do? Well, okay, so this is of course like I'm not saying anything on how to do such a thing. Yep.
Also, now that you've restricted this property, it might not be, C might not always exist.
Right. Sure. I mean, sure. You have all this kind of issue.
Okay.
So if you could do that, that would work. If you cannot, you cannot. Right. So the problem is. Huh? Right. So the context now is the context of reducibility. So in our case, the partial order is going to be the one induced by Weihrauch reducibility. So just to be sure that we're all on the same page, let me just briefly recap how Weihrauch reducibility looks like. It's a notional reducibility on partial multivalued functions on represented spaces in general, but for us it's going to be enough to talk about the vector space. So I will use interchangeably the word computational problem or multivalued function, because like we can see a partial multivalued function as a computational problem in the sense that you take the input to be any element in the domain and the output to be any y which is in f of x. Again, if you're familiar with this, you know that more general spaces can be you can talk about a function on more general spaces, on represented spaces. However, if you only care about the structure of the degrees, then talking about functions on the bare space is actually enough. Okay. And we will not really deal with represented spaces except for a few minor comments, but we can just glimpse it over them. So okay, the definition given G and F, we say that G is Weihrauch below F, if and only if there are two computable functions P and P, that works as follows. So you're given a P, which is in the domain of G, You want to apply phi to produce an input for f, so some element phi of p in the domain of f. Then you want to apply f and obtain some q solution for f for phi of p, and then you want to apply the function of psi to both p, the original input, and the solution q received from f to obtain a solution for g of p. I may end up saying things like forward and backward functional, and that's the diagram kind of suggests a way to think about the problem, and and also motivates the names forward and backward functional because phi goes forward and phi goes backward in a sense. A slightly stronger notion is the one of strong Weihrauch reducibility, and it's defined this like it's the case when C does not have access to the original input P, but only has to work with the solution provided by F. Okay, now let me introduce what are the first order problems. This is a definition. So let me remind you that when you want to talk about functions with codomain n, well, you can phrase them as problems on the bare space, essentially identifying a natural number with all the strings that begin with that natural number. So in other words, a function f with codomain n can be identified with the function that takes an input n input for f and just produces any q which begins with a solution for it. And you would like to call them first order problems. However, in many practical situations, it turns out that having such a strong constraint on the codomain, so requiring the codomain is exactly the natural number, it's kind of too strong. So we picked a slightly weaker definition, which is like, okay, if a function has codomain y, and this y is such that there is a computable injection from y to the natural number with computable inverse. So essentially, it's like effectively a subset of the natural numbers, if you want. Then we say the G is first order. Okay, so that being said, I would like to define the so-called first order part of a problem. The definition, however, is a little bit technical, so I feel it's better to, instead of giving the definition right away, we first prove the following problem, which also answers Joe's objection about the definability of the property that I care about. This is a theorem proved by Damir Zafarov, Reed Solomon, and Kita Yokoyama, and kind of motivates the whole thing. So the theorem says that for every f, there is the strongest computational problem G with codomain n, which is Weihrauch below f. In other words, there's maximum is well-defined. Well, okay, so let's try and prove it. Okay, so fix G with codomain n and assume that it reduces to f via two functional PMC. Now, this is the picture I showed you a moment ago of a generic reducibility, right? Nothing really weird is going on up to now. And by definition, we have the phi has to map an input P for G to an input for F. Now, the trick is that essentially given P, we can uniformly compute an index for a continuous function, so an index in the bare space, for the function that maps Q to psi of PQ. This is very easy, like this is just the universal Turing machine theorem, right? Now, since G has codomain n, what we have is essentially that the solution for GOP has to be essentially computed by, well, this is the functional, this is the W here is the functional that we just computed, so essentially it's just phi of PQ, and since we said the natural numbers are represented by just the first bit of, but the first digit of a sequence, we only care about what is produced by this functional in 0. Okay, so So this is essentially what we're trying to do. We'll say, okay, we don't really need the whole thing, we just need the first bit. And this motivates the following definition, which, I mean, can be made more general, but for now, this is all we care about. We can define it one f, which will be the first order part, as a functional that takes an input, well, an index for a computable functional, for a continuous functional, and an input for f. And just, well, intuitively, what it does is just computes f, apply the functional phi w, and just stops the first digit. Okay, now with this definition, it's kind of easy to see that, well, this definition works, right? It's clearly reducible to f, because if you're given a solution for f, you just apply the functional and stop at the first digit. And it clearly computes g, because that's the way we built it, right? We built it to compute g. And it's flexible enough to compute any g, in fact. Right, so to recap, this is the formal definition in general, which again, it's a bit technical, but like, I hope the proof of theorem kind of motivates the definition. The input for the first order part is just a pair, where the first input is the index for continuous functional, and the second one is an input for f. And what it does, well, it just, again, intuitively, it applies f, then applies the function to whatever solution you're given, and stop at the first digit. Okay, this is a definition. Let's see that actually it works as we would like it to work. So, formally speaking, it's an interior operator. It's it's idempotent and always produces something weaker than f. And also, it's monotonic. It's monotonic in particular degree theoretic, and so it kind of matches the original picture of producing something in the lower tone in a degree theoretical way. Okay. Now, before we move on, I would like this is a little bit technical, so I would like to kind of rephrase everything in a way that's maybe more intuitive, and it's actually the way I usually think about it when I have to work with that. Which is essentially saying that the first order part corresponds to the problem of computing sufficiently long prefixes of solutions. And
Possible to give two things who have first order parts which are incomparable naturally?
yes,
Will you do that eventually?
if you want.
I'm just curious, right? I mean, they almost looked at like the first order parts are all the same. It's just finite information.
No, I mean,
That's pretty.
pick two first order problems, sure. Okay. If you pick up a first order problem, then the first order part of a first order problem is going to be solved.
Right, sorry.
The first order part of a first order problem. So pick any function with codomain ends. Pick two of them incomparable, right? Those are two first order problems, and they are incomparable. And their first order parts is themselves, because they are problems with codomain natural number. It's a kind of trivial example.
Yes.
maybe not satisfactory.
Go on, let's go ahead.
Okay. Maybe I can give you better examples. Anyway, so the idea is that you can rephrase everything in saying that the first order part is actually the problem of computing sufficiently long prefixes of solution. And why is that? Well, that's just because, okay, this is the diagram I showed you a moment ago in proof of why G reduces to 1F, the way we defined it. But by continuity, to produce the first bit, you only need the prefix of Q. You don't need the whole Q, you just need a sufficiently long prefix Qn here. Right, so you may equivalently think of F as the problem that, okay, I give you an input for F, and I give you a functional W, which is just a CE condition that tells you, okay, this CE condition tells you when to stop, when you have seen sufficiently much of the solution. Right. Now, I would like to make some examples, but to do so, I need to first introduce a bunch of problems. Don't want to spend too much time on this. Also because, it gets boring after immediately, right? But still, like, I need to talk about something. And few like important benchmarks in the variability are certainly the so-called choice problems, which can be phrased in their, let's say, more general way as simply as given a set which is non-empty, find a point in the set. And of course, the complexity depends on what is the set that you're gonna allow, what are the properties, how do you code such a set, et cetera, et cetera. So in particular, for example, we can think about choice on the finite element space, choice on K, just a set of K points. You can rephrase it without ever mentioning closed set or representation or anything. You can rephrase it saying, okay, given a sequence of K plus 1, just produce a number which is not enumerated in the sequence. Similarly, choice on the natural numbers can be seen, well, it's the same, but like now you don't have a value, you just have a sequence in the bare space with the constraint that, of course, there is a number which is not enumerated and you want to find it.
So these are finite sequences?
No, infinite sequences.
So there may not be a number that's.
Well, I mean, yeah, you assume that there is. You assume that there is.
Yeah, so that's.
No, it's like I'm trying to be quick. Don't want to be over formal over this, but like, yeah, of course. You assume that there is a number which is not enumerated and you want to find it. Choice in Cantor space is essentially, it should be closed choice in the Cantor space, but closed set in the Cantor space corresponds to trees, and so this can be rephrased essentially the way to phrase Koenig's lemma. Given an unbounded binary tree, produce a path.
What's the first order set?
I will comment on this. I will comment on which is the for sure part of this guy. For choice in the bare space, same thing, but now the tree is in the bare space, so much more complicated. And there are many variants of these problems. I don't want to mention them all. Let me just mention sigma 1 choice. In this case, on the natural number, in this case, the input A is not a closed set, but it's a sigma 1 set. So intuitively, you can think of it as, well, deciding membership is a sigma 1 problem. So you can say, okay, given the list of trees, find the index of an ill-founded one. Being ill-founded sigma 1, therefore, it's like picking an element in the set.
Okay.
Yep.
CK, that's
Sure.
the first one, right?
Sure.
So are they, if I have C3 and C5, are they comparable?
Well, C3 you just C5.
But it's strict.
Yes. But for example, if you consider C2 and consider say LPO is the problem of checking whether a string is equal to constant 0 or not. Well, sorry, C3, not C2. Take C3, okay. Take C3 and LPO, they're incomparable. And they're both first order problems.
PO is just, it's all zero.
LPO checks whether a string is all 0, yes. Yeah, if it finds 1, it says no. If it doesn't, it says yes. Something like that. All the equivalent reformulation.
C3 and then
Yes.
C2 and that's it? Or-
No, C2, no, you can. This is. Okay, a couple of things. I don't want to mention too much about operational problems. There are so many. But at least a few of them are going to be relevant to the talk. So the parallel product, in particular, the first one is just binary parallel product. It consists of solving f and g in parallel. So I give you two inputs. You want to solve them all independently. There's the star, which consists of solving finitely many instances of f in parallel. So and there's an important detail here, which is that you have to commit in advance to a certain number of f. So you say, for example, 10, and then 10 inputs for f, and you want to solve them all in parallel. We will see that the fact that you have to commit to a certain number is important. There's the infinite parallelization, countable case. There's a compositional product, which I mean, it's kind of a tricky one. It consists in a, let's say, series composition. So you first solve G, then you do something possibly computable, some computable operation to whatever solution you're given of G, and then you want to apply F. So it's of course stronger than the parallel product. There's the jump, and people in Madison have already heard me complaining about the jump. So I will not, mention too much in this situation. Let me just say that this operation that, like, the input for a jump, or let's say the name for an input or a jump is just a sequence converging to an input for F, and the solution is just a solution of F of whatever limit you get. Okay. The reason why people are complaining is because, like, this is not a real jump, it's not degree theoretic, it's not like there are some issues, but like for what we care in this talk, it doesn't matter. Sure.
This is just converting sequence to some name.
Yeah. The input is just a conversion sequence to name. So that's why it's harder, because of course you don't have access to the name directly, but you have just a limit conversion to the name.
So you need like the output piece. The one thing I like is square root 2.
Square root 2. What?
Is it, well, I mean, see, but f of x has got to be real. I mean, an actual.
F of x is just whatever f is producing, right? Take any f. Instead of giving you the input directly, I give you a sequence converted to an input. Okay, now let's list a few examples and first order part and see how it works. Okay. Now the first order part is relatively new as an operator. However, like in the literature, you can rephrase all the results in terms of first order part because, like, it implicitly we're characterizing it. So one example, very easy, is like in the case of f is densely realized. Densely realized, it just means that for every p, f of p is dense, so the set of solution is dense. Well, in that case, the first order part is just the identity, just uniformly computable, and that's because, like, if you think of the first order part as how hard it is to compute a prefix. Well, if you're dense, anything can be a prefix, right? So you can just try. You try them all. Eventually, your functional it's going to converge to something, and that's going to be okay for you because there's going to be a solution extending that finite string HP. And so, in particular, for example, finding a non-computable point, non-arithmetic point, or Martin-Loff random point, or whatever. They are all for all of them. The first order part is trivial. It's uniformly computable. Okay, an old result by Vasco Bratka, Guido Gradi, and Alberto Marcone can be rephrased as saying that the first order part of lim, which is finding the limit in the bare space, is choice of natural number. Why is that the case? Well, like very briefly, the idea is that if you're given a sequence in the bare space, for each component, you can find the limit in that component with finitely many mind changes. It's just the limit on the natural number, so you only need finitely many mind changes to find the limit. And since you want to compute the prefix of the limit, you only need to do it for finitely many components, let's say finitely many rows, and therefore, since being reducible to choice of natural number exactly corresponds to being uniformly computable with finitely many mind changes, that's how you get one reduction, like the fact that the first order part is below choice of natural number. The other reduction follows from the fact that, classical result, lim is just the parallelization of choice in the natural number, and therefore you get the other reduction and you get the equivalence. For weak Koenig's lemma, and also, like, in fact, even weak Koenig's lemma, there's a reason that, like, the same guys that introduced the first order part gave this as an example and proved that the first order part corresponds to the finite parallelization of choice on 2. And now we're not going to do the proof of this because it's a little technical, and we'll lead us astray. But the idea is that you essentially exploit the fact that choice that the counter space is compact, and therefore you can find a bound to how many instances of choice on two you need to solve. This, of course, doesn't work in the case of the Baire space. Now I'm saying that this result is mine together with Gin law and Arno, but in fact it's just an exercise, to be fair. It's just that we were maybe the first one phrasing the thing in these terms. But the idea is that, okay, for choice on the Baire space, you cannot really exploit anything except just saying, okay, find a sufficiently long string in the tree which is extendable, which extends to the path. Being extendable is a sigma 1 condition, and therefore you get sigma 1 choice on the natural number. But as you can see, like all of these results, they're kind of, independent of each other. Each one uses a different technique, different ideas. So like, first of all, natural question now would be, how about parallel 1 comprehension? Parallel 1 comprehension can be phrased as saying that, okay, can be phrased in many ways, but one way could be, I give you a parallel 1 code for a set of natural numbers, you give me the characteristic function. Or equivalently, it can be said, okay, I give you countably many trees, and you tell me for each one of them whether it's ill-founded or not. And that's essentially what's written here. Well, WF stands for well-founded. It's the characteristic function of well-founded trees. So for I give you a list of trees, and you tell me which are the ill-founded and the well-founded ones. Right. Everything we said so far doesn't really gives any hint on how to deal with this. And in fact, like the question is like, what can we say in general? Can we actually work with this thing in a more algorithmic way, in a more comfortable way? So as you may notice, in many cases, many of the cases that I mentioned, it turns out that F can be written as the parallelization of something which is first order. So F is equivalent to G parallelized where G is first order. So a natural guess would be, okay, but like, can we say something in this situation? Can we actually characterize the first order part in terms of G? Well, okay, notice, for example, lim, it's the parallelization of choice on the natural number. Well, we proved that its first order part is choice on the natural number, which is choice star. It's equivalent to the finite parallelization. Same thing with Koenig's lemma, it's the infinite parallelization of choice on 2. And we may guess that its first order part is just finitely many instances of choice on 2. This is a reasonable guess. So you may guess, okay, maybe the first order part of in this case, you can already say that the first order part is G star. However, this doesn't quite work. And as a counterexample, consider the following. I give you a sequence of trees, and you have to say, okay, return 0 if they're all well-founded. And if not, you have to tell me the index of an ill-founded one, or essentially I plus 1, well, I mean, just to avoid conflict with 0, like I plus 1 is not really a problem. The thing is that either you tell me that they're all well-founded, or you tell me the index of an ill-founded one. Okay, now observe this. This can be solved by one comprehension, because you just say, okay, the first instance, like the first question that you ask is, are they all well-founded? Is it true that for every E, the I3 is ill-founded? This is a final question. If yes, then you're done. And if no, well, all the other questions that you ask is whether the I3 is ill-founded or not. And so if not, then you know that there's going to be a tree, which is going to be ill-founded, and you just look for it by unbounded search. So parallel comprehension can solve it, but you cannot do the same with WF star. So as long as you can meet to any fixed number of instances of WF, so instances of to any finite number of parallel 1 question, then essentially you're screwed. You're not gonna be able to make it. So the idea is essentially that the problem that makes us this problematic for us, the thing is problematic for us is that we need to commit to a certain bound. We would like to relax this condition. And that's essentially what we are trying to do now. We introduce a new operator that kind of fits. The idea is to fit essentially in between the finite and the infinite parallelization, something we call the unbounded finite parallelization. And intuitively, the idea is that it has to work like the finite parallelization, but you don't want to commit in advance to any specific number of calls. Well, to formalize this, well, again, it's a little bit tricky and it's annoying. It's technical definition. It's not easy to work with. But the idea is similar to the one of the first order part. The input is one functional which should tell you when to stop, and countably many questions, countably many instances to ask. And the solution is going to be just finitely many. But like, how many? Like, what is this k here? Well, this k is, again, the condition you pass as input is the one that is like, it's like the index of a functional tells you when to stop, intuitively speaking. So you have a functional, you wait for it to converge with only finitely many columns of the solution, and if it does, then you're happy. And if it does not, then okay, you need more maybe. And of course, you always have to assume that the input emits some, that the functional picked in input has the property that for some k it is actually otherwise it's not in the domain. Okay, this is a definition. First thing that you want to be sure of is that it actually works. So yes, it's a degree theoretic operator. It's idempotent and always going to produce something which is stronger than F. So it's called closure operator. And in particular, and moreover, it fits nicely between the finite and the infinite parallelization. So it kind of, up to now, it kind of works as we were hoping it to work. So let's see how to phrase problem, like how does it behave with respect to the first order part. Okay. So the first result here is that if you want to compute the first order part of a parallelization, well, you might as well just consider finitely many columns. The idea is that, well, okay, the proof is fairly simple. One direction is trivial, just follow from the fact that the first order part is degree theorem. So one direction is not interesting. The other one, of course, is when you want to say that the first order part of the parallelization, which apparently is stronger, is actually the same as the first order part of the unbounded finite parallelization. The input is that okay. The idea is that okay. Say that you have the solution for the parallelization. The solution for the parallelization is, countably many columns, countably many solution one for each xi. When you do the first order part, you actually have to pick a prefix of a solution. A prefix of a solution is usually, since you all usually code strings by dovetailing, you do the infinite join by dovetailing, it turns out to be something like this, right? Some sort of triangle. But in the moment you do something like this, well, you're not only selecting a finite prefix, you're both selecting finitely many rows and finitely many columns. So, in other words, this functional here, which is the input for the first order part, actually already tells you how many columns you need. Not only, the moment you select a prefix, it's also selecting finitely many columns. So it actually works. It actually works for us for the use part as well. And with this in mind, we can actually formulate this theorem, which gives a neater characterization. So whenever F is the parallelization of something which is first order, which turns out to be first order, then you automatically can say that the first order part of F is just the unbounded finite parallelization of G. Okay, and moreover, this is kind of a nice addition. Like under this condition, which is relatively weak, it corresponds to being a cylinder. If you're familiar with it, if not, it just says, well, just take it as a technical condition, not very important. But if you have this under this assumption, then this same result leads to jump. So if you, instead of taking F, take the nth jump of F, well, its first order part is gonna be the nth jump of the unbounded parallelization of G. Yep.
Why do you think G refers to W in the first line there?
What do you mean?
Why do you need G refers to? I mean, is it necessary?
Yes.
Okay.
I mean, what will be your guess here? Just take F to be parallelized. Yeah, it doesn't really work.
Okay.
It doesn't really work, but I mean, it's in fact something that I will see. It's in fact something that I may have mentioned if I had enough time, but the question is like, okay, essentially this result is saying that the first order part and the U star, they actually, oh, and I touched it, but nobody saw it, so it's okay. The first order, I'm being Italian, okay. The first order part and the U star actually commute, right? So a natural question would be like, okay, do you need it, like essentially the question by some, do you need G to be first order in order for this to work? And this is a good question, and the answer is no. However, I mean, I'm not gonna go through that. Let me just skip this, okay? But let me go to the end, right? In some cases, you can work it around and have a result like this, even for F, which is not first order. So some sort of commutativity with the first order part, even for F that are not first order. For one example here that I mentioned is in the case F is finitely valued. It can work as well whether like if F, if I remember correctly, if F is single valued, that would work as well. But again, it's very specific and it's like adapting the argument in such a way to make it work. But it's not really an interesting case per se. And in fact, given that there is a counterexample here, I would say that in general, this doesn't really generalize to any function. You really need to be first order. I mean, the interesting case is when F is first order. Right, okay. So applications now, okay. We already mentioned lim, right? So lim, we know it's the parallelization of choice and natural number, and it's the parallelization of LPO, which is the problem I was mentioning before, of checking whether a string is constantly 0 or not. You can think of it as answering a single sigma 01 question or pi 01 question. And lim is the parallelization of both of them. And given that a Neumann and Pauli, they prove something stronger, which implies in particular that choice and natural number is actually equivalent to its unbounded parallelization. You at a glance get that the first order, you get a characterization of the first order part of lim just by saying that, oh, it's choice and natural number, it's actually LPO U star. And of course, lim is fairly strong from the point of view of strong reducibility. So you also have that this generalizes to jumps, and like only once you get the characterization of the first order part of the nth jump of lim for every n. And same it goes for pi-1 comprehension. We mentioned that it's for the parallelization of WF, which is the problem of checking whether a tree is well-founded. So in one shot, you already have a characterization of what is the first order part of pi-1 comprehension. Pi-1 comprehension lives in a very, high level of the hierarchy, fairly unexplored territory. So nobody really knows exactly what's going on there. So this already gives you a characterization in a very general and automatic way. You don't really have to deal with what is pi-1 comprehension exactly. Right, so there are 10 minutes left. So in the 10 minutes left, let me mention a few words on this operator, this called diamond operator. Essentially, it's an operator that roughly corresponds to using a multi-valued function as an oracle in the computation. I say roughly because there are some details, and the definition given by Arno and IK is like terrible. It's like terribly complicated, and they also give it only in a specific case. However, there are many equivalent versions of it. And the one we picked in our paper is the one actually given by Hirschfeld and Jokic, which is a game theoretic characterization on how this diamond is supposedly work. They call it generalized uniform reducibility or generalized Weihrauch reducibility. So let me break down how the game goes. Essentially, the idea is that player one plays the role of the oracle, and player two plays the role of an algorithm trying to solve G given the oracle F. So the first move is just an input for G, the one that G has, so that player two has to solve. And player two can either just solve it, okay, just say, okay, G is computable, so I can compute a P computable solution Q for G of P, and that will be the end of the game. Or if it doesn't, well, it can play, say, an oracle call. It can make an oracle call, so it can play a P computable X1 in the domain of F. Well, now it's turn of P1. P1 just plays, okay, what? Well, it plays a solution. Just plays some Y1 in F of X1. Yep.
When you say people are is there uniformity there enough?
Well, this is a game. Then if player two has a computable strategy, computable winning strategy.
That's just playing people saying, I want this
Yes.
with this index. Uniformly, right? Player two strategy has to be computable.
Well, for the moment, no. For the moment, it's just the vision of the game. But yes, I will assume that the strategy is computable and therefore like uniform, right?
Okay. Got it. Okay. So the uniformity comes when you.
Well, when you answer the strategy is computable, right? Exactly. Right. So player one plays with the solution for F, and then again, player two can either compute now a solution for G and win, or it can play another oracle call, and this goes on, right? And then this goes on forever until player two declares victory. So until player two declares that it can actually compute a solution for G, and therefore he wins. Otherwise, player one wins. Player one wins is not a very interesting situation. The one we care about is when player two has a computable winning strategy, and it's the case when you actually have a Weihrauch reduction or uniform reduction of G to F diamond. Right. So the idea here is that essentially this diamond operator corresponds to using F in series arbitrarily many times, but a finite number. So in particular, if F, like, okay, what is a solution for F diamond? Well, a solution for F diamond is just run the game. It's just a series, that's just a list of answers of oracle solution given by player one. And in that case, if F is first order, then F diamond is first order as well. Right. So you may okay. So as I said, diamond is essentially an unbounded compositional product. So given that the U star is an unbounded finite product, finite parallelization, you may ask, what is the relation? Like, is there any situation in which two are equal or different? Well, of course, doing things in series is stronger than doing things in parallel. So the diamond is always stronger than the U star. But is it possible for them to be exactly the same? Now, we couldn't really come up with any complete characterization of when the two things agree, but we came up with some sufficient conditions. And in particular, this one is the one we will be using afterwards, saying that under certain conditions, so if F is total with codomain N, and such that its graph is pi 0, 1, then the U star and the diamond actually agree. The graph being pi01 corresponds to not being the graph being sigma 01. So in a CE way, you can tell when a guess is wrong. So the idea is that you want to sort of run the game, guessing what could be the possible solution given by the possible move played by player one. So guess a possible solution of the oracle call. And since the graph is pi01, if the guess is wrong, in final time you will see it, and you can discard let's say the branch of the tree. That's the idea of the proof. Besides, if the range of f is actually fine, like you have a bound, you know it's k, the bound is k, then in that case you don't really need the U star. You don't really need the unbounded parallelization, but just the standard final parallelization would suffice in this because you can actually compute the height of the tree of guesses that you need to solve your problem. Let me skip this because it's just that was like just another sufficient condition under which the U star and the diamond agree. But let me just go towards the end of the talk. So now we can make more sense out of this problem here, because like the general solution would say that the first order part should be the U star of C2. However, given that C2 magically matches all the conditions that we said a moment ago, so its graph is closed and you can make it all under center assumptions, it turns out that it's actually that the first order part is actually just the time parallelization of choice on 2, and moreover this leads to jumps. So the jump of Weak-Koenig's lemma, in particular Koenig's lemma, is the first jump of Weak-Koenig's lemma. So this at a glance gives you the first order part of Koenig's lemma, for example, but also like all the other jumps. And you have a characterization of their first order part in terms of C2. Now again, for pi1 comprehension, you may wonder whether what's the strength of this guy here? What's the strength of using WF in series arbitrarily many times? Well, it turns out that it's actually just equivalent to using arbitrarily many times in parallel. And this is strong, it's certainly stronger than doing it finitely many times with a bound. And yeah. So one last thing to conclude the talk is Ramsey, because you cannot miss. So this is a classical result by Vasco Balcantaina, Rakotoneina, which I mean they present a bunch of results in the Weihrauch degrees on the Weihrauch degrees of RT and K, varying N, varying K, and similarly for stable Ramsey theorems, and so on and so forth. So this is just what they proved in their paper, and therefore, like as a corollary, now we jump in for free. We know, okay, I mean, we know the first order part of Weak-Koenig's lemma and jump. This is first order, so the first order part is this one. So we, for free, have a bounds on the first order part of Ramsey and stable Ramsey theorems. Things get a little bit tricky now because we would like to say a little bit more on the two the two reduction. We don't know whether they're strict or not. Yeah, and that's part of the question. And in fact, they left it as open as a question whether what's the exact strength of. I mean, you can rephrase their question in terms of the first order part of RT22. In particular, they asked whether the jump of choice of natural number reduces to RT22, and we answered the question in a negative way. This actually generalizes to this is a more general result because it involves arbitrarily many jumps, not just the first jump. This is a theorem that we worked it together with Arno, and then essentially, Arno gave us like a neater proof of our idea essentially, And kind of allows us to answer that question, at least in case of RT22, or let's say Ramsey theorem for pairs, in which case we have this strict chain of inequalities. We don't have, unfortunately, better characterization, but this is very Ramsey-ish, right? To always be on its own and never be comparable with anything, right? So, so it's like, okay. Yeah, so we leave this number question, and yeah, there's a few references. Thank you very much.
Questions online or any place? Or someone who talks about it, I don't know. Let's thank the speaker again. Okay, so we're gonna make a